Welcome. This question says a system consists of a body having a moment of inertia of 5 kg/meter squared, which rotates at 3 meters per second, 3 radians per second about its turning axis. What is the rotational kinetic energy of the system? So we can visualize an arbitrary object, and we have a rotation axis. You can imagine this thing rotating. And what I can say is the system has a moment of inertia of 5 kg/meter squared about that axis. And it rotates with a angular velocity which is equal to 3 radians per second about this turning axis. So what is the rotational kinetic energy? So we have K rotational, if you like, equals, I don't know. So we need an expression for rotational kinetic energy, and we may recall that translational kinetic energy was equal to 1/2 mv squared, where this was v translational. Well, using an analogy, rotational kinetic energy would be 1/2, and then the angular equivalent of mass is I, moment of inertia, and the angular equivalent of translational kinetic energy, translational velocity, is angular velocity. So then I say, okay, that means that my K rotational is equal to 1/2 times I, which in this case you're given, which is 5 times your angular velocity, which again in this case you're given. This is a very straightforward example. So K rotational is equal to 1/2 times 5 times 9. So K rotational would be 5 9s are 45, and 1/2 of 45 is 22.5. And the units, well, it's kinetic energy. So the units are joules. So here's the conceptual issue, and that is that it takes kinetic energy to get, and it takes work to get an object rotating, and the rotation stores kinetic energy. So for example, if I have an object that can slide down a smooth surface without rolling, and I compare it with the same object that rolls down the surface without slipping, then whatever energy I give to the objects at the top of the ramp will be used for the sliding object in only translational kinetic energy. But for the object that rolls down the ramp, I would split my initial, in this case, gravitational potential energy into translational Ke plus rotational Ke. And that has consequences for whichever one can actually travel faster translationally at the end. The sliding object, if there's no friction, moves faster at the end of its journey than the rotating object, because the rotating object has to use some of its initial mechanical energy to support the rotation. So there we have it.